All right. So, first of all, sorry for the late cancellation on Friday. I had something come up on Friday and over the weekend that kind of took me away from things. So, hopefully, we should be good for the rest of this week. I'll post, I think it's should be up on YouTube right now. I might not have it under the honors playlist, but I'll make sure it's there after class. It's just kind of two different examples that I worked through in Excel, kind of going over some things that you could see kind of pop up on the exam. Today, we'll kind of start working through some practice exam problems. So I've got practice exam A up there. I'll post some additional questions that we'll work through, Friday's class as well. I would say if you're studying, other than those practice problem questions, really thinking about, and I'll get up an answer key that's, it's going to be different for everyone because you have different data set, but I'll get up my data set, I guess, and how you would answer the questions for that individual assignment, just so if you did get things wrong, you have a correct set of answers to make sure that you can kind of study from as well. So I'll get that posted sometime tomorrow. And then going back through kind of that last Connect assignment will help going through probably, like I said, I think the practice problems we'll work on this week are really going to be the most important thing. Going back through some of the lectures would be important as well, just making sure you can kind of understand, especially when we were kind of working through this stuff in Excel. I showed you, because really a lot of this linear regression is going to be I give you output and then I'm asking you questions based off of that. So I'll try to point out as we talk through things this week how I would like convert, even if we look at something that isn't specifically written out as a question, how I could ask a question that's similar to that content, how that would look as like a multiple choice question or a short answer question on the exam. So the exam will be about 50-50 probably. I think maybe a little bit less than 50% multiple choice. So kind of at least 50%, maybe a little bit more would be kind of short answer. So you're going to have to upload a lot of your work for those. I plan on having kind of the length of the exam being 2 hours. So you'll have quite a bit of time to work through all the problems. There won't be near as many multiple choices, kind of the previous exams, probably only like 10 to 12. I haven't finalized the final quite yet. But once I have that finalized, I'll give you the specific breakdown of multiple choice and short answer. And so I think that should cover everything. Are there any questions for me before we kind of jump into some of these problems? Where's the chat? There it is. Also, since all the assignments have been turned in, I'll start, once I get all those graded, I'll drop the lowest and then kind of change canvases around a little bit to post like what your final score in each one of those kind of assignment categories was. So you'll have an idea about where your grade is at in the class. You can play around with that, figure out your grade tool to see what you need in the final to get certain grades. Okay. All right. So let's go. There's no questions. If anyone is worked through taking a look at this, if you want to start with a specific question on here, let me know. There's quite a few. So you got 25 different short answer kind of style, a few multiple choice questions, but we can start with any that someone has specific questions on. Otherwise, I'll probably just kind of start from the beginning and we'll start working through towards the end. Give a second or two here. Okay. All right. So kind of going back to after the second exam, so we're going back quite a ways here, but we've got this example where we were curious about whether or not people consume fewer calories after calories were posted on the McDonald's menu. We sampled 42 people. We then calculated this difference variable, which was just their after calories minus their before. So you find that the average difference in calorie consumption was negative 50. You have a variance on that difference of 22,500. And I'm giving you kind of the hypothesis test here. So we want to test for whether or not calories have decreased, right? Whether or not this difference, the true difference, is less than 0, right? Because if it decreased, after would be less than before, and this difference would be negative. So that's what we're going to test for. So we assume the opposite is true. We get a left-tailed test here. We've got the significance level we want is 5%, so the alpha of 0.05. So calculate the test statistic for this hypothesis test. So we're thinking about, have this formula sheet up here. Kind of here's our matched pair equations. So here's our test statistic. Right? So we take the sample difference we found divided by the square root of the variance over the sample size. This should be a really easy question, right? Calculating this test statistic for a matched pairs example, all we're doing is plugging in our three values, right? So negative 50 divided by the square root of 22,500 divided by 42. Now, if you notice, remember, the denominator of a test statistic always represents some type of standard deviation or standard error or variance. And so all of those are going to be positive, right? Because we're squaring deviations, everything's always going to be positive here in the denominator. So if we look at this sample difference, it's always going to tell us the sign of the test statistic. Here we've got negative 50. So right away, we know the answer can't be positive. From there, it's a matter of plugging everything in. If we do that, we find that we get kind of this negative 2.16. I mean, I can't really help much on this one other than like once we identify we're looking at this sample difference. I mean, it's actually easier probably than the last exam because we really only have one test statistic equation. Other than that, when we're looking at coefficients. Okay? So negative 2.16 here. Let's assume that instead we found negative 2.5. Using this null alternative hypothesis, what would the critical value be in the outcome of the test? Well, first of all, we have a left-tailed test. Right? So when we're thinking about this, everything on this exam, we should be using the student t-distributions. We don't have any proportion examples. We don't know any population variances. So we're thinking about what value would give me kind of that alpha of 0.05 in that left tail. We know that the student t-distribution is centered around 0, so that if I have a left-tailed test, our alphas are relatively small. The area to the left of 0 would be 0.5. The area we want to the left is 0.05, so we know that we're going to have a critical value to the left of 0, so we know it's going to be negative. So we'll go to that student t-distribution, that table. Now, our sample size was 42, so the formula sheet reminds us that our degrees of freedom is simply n minus 1. So 42 minus 1 is 41. We wanted 0.05 in the tail, so 1.683. Now remember, the student t table tells us everything as though we're looking at that upper right tail. We had a left-tailed test, so we were looking at the lower left tail. So everything's going to be the same because it's a symmetric distribution. So instead of 1.683, right, we're going to have that same value, but negative. Right? Thinking about our rejection region being, if we see any test statistic that's more extreme or greater in absolute value than our critical value, we can reject. If it's not, then we would fail to reject. So I gave you that assumed true test statistic of negative 2.5. So if I plotted that, he's somewhere over here. So we're in the rejection region. So negative 1.683 is our critical value, and we would reject, right? Because that test statistic's in the rejection region. Okay. If I instead had asked you for the p-value, right? I maybe have enough room here. The p-value would be the probability I saw that test statistic or anything more extreme, so anything to the left. So if I look up at degrees of freedom of 41, my test statistic in the table, I should be able to get what that p-value is. Now the problem is, if I go to that student t table, at degrees of freedom of 41, I don't see any negative values. Well, remember, it's a symmetric distribution, so we kind of could look up 2.5, but I still don't see 2.5, but it's in between these two values. So I know that my p-value is going to be somewhere in between 0.01 and 0.005. So this was a scenario where I can't give you the exact p-value, but I can tell you that the p-value is somewhere between 0.005 and 0.01. Okay? So in that scenario, we only reject if the p-value is less than alpha. My alpha was 0.05. Well, if my p-value is somewhere in between 0.005 and 0.05, it's definitely, If it's in between, somewhere between 0.005 and 0.01, it's definitely going to be less than 0.05. So I would get the same rejection decision if I use the critical value approach, which is that I reject. So that's kind of going back quite a ways. Some more like specific hypothesis testing stuff. Once we got to linear regression, kind of was always the same null hypothesis. So that was a little bit of a review of stuff that came from a while ago. So any questions on that before we kind of keep moving? Okay, good with that one? Okay, so that was what? And also, one thing I had mentioned, for left-tailed tests, our critical values are always negative, so we could have ruled out this guy right away. So the next thing we haven't talked about for a while, kind of going backwards, is this Anova testing. Right? So let's say I had this data where I had kind of the average, and here I believe this is kind of thinking about the average percent of people who, or so no, this was the BMI, sorry. I didn't give a little bit of a predecessor here, but the question refers, these are BMI values. So this is the average BMI for males who never smoke, average BMI for males who used to be smokers, and the average BMI for current smokers. And then the kind of the same thing for females here. So we see that they're all pretty similar, but there are differences. Right? So if I run this Anova test, so if I'm in Excel and I select this data and data analysis, I know two-way factor ANOVA without replication, and I run it, I would get this output. Right? So I've got my rows and my columns here. So here's my p-values associated with both of those. Okay. So what can be said about the variations? So this one I left open-ended, somewhat of a short answer question. So what can be said about the variation in BMI at the 95% level in respect to gender and smoking status? Well, my rows, right, were gender, kind of male, female, and I found a p-value of 0.66. Well, a p-value of 0.66, that's not less than any of my alphas, 0.01, 0.05, or 0.1. So I would fail to reject the null, which really the null here we can think about is that the mean holding constant gender, sorry, nope, I'm looking at the rows. The mean holding constant the smoking status of the individual doesn't vary across the rows. So what we're really saying is that if we fail to reject the null, we're saying that even holding constant someone's smoking status, there's no difference between the genders in BMI. Okay? So we can't say that there's any significant difference in BMI related to gender holding constant the individual's smoking status. Now, potentially, right, if we were to see maybe a p-value that looks something like this, so maybe this one's a little bit more interesting. If the p-value was, say, instead 0.06, well then, kind of my p-value being less than alpha means I can reject the null. Well, 0.06 is less than 0.1. It's not less than 0.05 or 0.01, but it is less than 0.1, so I could say at the 90% confidence level or the 10% significance level, right? And here I'm asked specifically about the 95, right? But I could say with 90% confidence that there is variation across the rows, right? Or there is variation in respect to gender with BMI, holding constant someone's smoking status, if the p-value is 0.06. Now I can't here, right? Remember it was 0.66, but trying to give you something maybe you would see on the exam a little bit more of an interesting p-value is that here at the 95% level, well, 0.06 is not less than 0.05. So I would still be failing to reject the null, or said differently, remember the null is that across gender this is the same. So if I'm failing to reject that, I can't say that the BMI has any difference in respect to gender. Same kind of idea with the columns. I have a very high p-value there. So what can I say about the variation in BMI with respect to smoking status? Well, holding constant someone's gender, if the p-value is 0.44, I'd be failing to reject because that's not less than 0.05. Right? So I can't say that there's any difference in BMI in respect to someone's smoking status, even holding constant their gender. Okay? So that's how we kind of read these Anova testing tables. We look at the p-value associated with either the rows or the columns. If the p-value is greater than alpha, what we're really saying is we fail to reject the null, and we start out assuming that the mean is the same across all these different factors, right? Across smoking status or across gender. So if we fail to reject that, we're really saying there is no difference. If we can reject it, like if we had a p-value of 0.06 here, then we could say that there's some variation in respect to whatever that row, the row headings are, or whatever the column headings are. But here we had an example where we couldn't. Right? So it's not a super interesting example here. That's why I kind of changed the p-value to give you maybe something a different example that you could see on the exam. Okay. Any questions on that? No, we had that was problem 1 of the individual assignment as well. So when I post that answer key, that will be, that one I won't have to use kind of my own data set for, but you'll have the correct answers there to know how to evaluate that. Okay. Any questions on that before we kind of continue to move on to some more simple linear regression stuff? Okay. So we've looked at this data set quite a bit, or maybe not quite a bit, but I think I've played around with kind of this idea of using this y variable, which is wage, and then looking at how these other things impact wage. Okay. So let's say my dependent variable is wage. So the dependent variable is my y variable. My independent variables are these right-hand side or my x variables. So I included education, the units is years of schooling, experience, years of experience, age, year, measure in age or years, and then gender, which is 1 if they're male, 0 if female. Okay. So I hid the t-stats here, the test statistics. But if I wanted to calculate these test statistics, which is essentially problem 5, now problem 5 specifically asks you about age, but you could really come up with a test statistic for any one of these. All the test statistic is, if we look at this formula sheet, and there's some formulas on this formula sheet that you're not likely going to use, just some things that we've talked about, how to get those F stats for the Anova table, even though you won't have to do that because you're always going to just have the output. We do have an equation down here for our test statistic for coefficients, which is just take the coefficient estimate and subtract the standard error Excel gives you. So to get my test statistic, all I would do is take this coefficient and divide it by the standard error. Right? Let me zoom in here just a little bit so it's a little bit easier for us to see. Okay. So for the age coefficient, I would take negative 0.018, sorry, negative 0.019 and divide it by 0.083. Okay. If I do that, I believe I should get negative 2.29, right? And if you open this file, notice if you click on this blank space here, you can move that out of the way. Okay, so just click on this blank space, and you can move it out of the way. Shout out to Taylor Swift. So anyways, sometimes I think I'm funny and I'm not. So anyways, you could try to do this for every single variable here and reproduce these test statistics, and that might be a good exercise or good practice. Okay. So we skipped 4, but 4 was what's the correct interpretation for the coefficient on education? Well, the interpretation of any one of these coefficients, what we've really done, I'll just type this out above here so we can have this as a visual as we're talking through it. What we're really doing is we said the wage, right? And I believe, sorry, to be more specific, the hourly wage is a function of education, experience, age, and here I'll call the gender variable male just to make sure we remember when it was 1, it represented that individual was male, 0 was female. Okay. So the predicted hourly wage, right? If education goes up by 1 unit, and 1 unit here was the years of education, so 1 more year of education would predict that this y variable, hourly wage, goes up by whatever B1 is, whatever the estimate we have for B1 is. So education 1.23. So for every additional year of education, we would predict hourly wage goes up by $1.23, holding constant everything else in this regression, right? So first of all, we should be looking for that 1.23 coefficient. So A doesn't make any sense. Coefficients don't represent averages. And so then there, it's holding everything else constant. every additional year of education is correlated with a $1.23 increase in hourly wage. Now, here this is a multiple choice question. I wouldn't be, you should expect to be able to write this out as a short answer as well. So knowing that general interpretation will be important, okay? I think I skipped some other things here. So I'll add in some additional questions as we work through these, just so that potential questions I might ask, you also know how to answer. So you should be able to interpret all these other coefficients as well. They should be pretty easy with experience and age, because it's just those are measured in years as well. So it would be like an additional year of experience increases the predicted hourly wage by 41 cents or $0.14. Being another year older predicts that your hourly wage would go down by 2 cents. And then here, this one's a little bit tricky. Remember, this gender variable is 1 if they're male, 0 if not. So if the individual is male relative to female, right, because that would be a 1 unit change going from 0 to 1, we would predict their hourly wage is about $2.29 higher. Now we can make all these interpretations, but if we look at these p-values, which of the following variables can I reject the null for? Now remember, this null hypothesis, hypothesis is always that the slope coefficient is equal to 0. If I can find that the p-value is less than alpha, then I can reject that, right? Or I can say that there's a significant relationship between that variable and the y variable, hourly wage. So look at my p-values here. Let's say I wanted to say with 99% confidence, right, or the 1% significance level, which of these can I reject the null for? Which of these variables? Well, if I look here, let's just focus on these 4. We'll worry about the intercept in a second. So for the education variable, well, that p-value is less than 0.01. So I could reject the null and say there's a significant relationship between education and wage. 0.005 is less than 0.01. So I can say there's significant effective experience on hourly wage. Age, because it doesn't really make sense that as I get older, my hourly wage would go down. Well, yeah, that's the interpretation. But if I look at the p-value, I'm so far away from being able to reject the null, which is that there's no relationship between age and hourly wage here. And if I look at the gender variable as well, even though there's quite a sizable effect of being male on hourly wage, the p-value isn't less than even 0.1. It's definitely not less than 0.01. So even with 90% confidence here, I actually would fail to reject the null because that p-value is not less than alpha. So I can't say there's a significant relationship between gender and hourly wage or age and hourly wage, but there is a significant relationship between experience in the hourly wage and education in the hourly wage. Okay? So you should be able to go through output like this and determine which variables you can reject the null for. And if you can reject the null, what you're saying is there is a significant relationship between those variables and whatever your y or whatever your dependent variable is. Okay? Any questions on that? And one thing that's interesting about this is, we have a relatively low number of observations. Usually, when you have a small number of observations, it's harder to get kind of low p-values, right? Okay, so, and this is actually specifically referring to that 99% level. Which of the following, other than the intercept, could we reject the null hypothesis for? Well, we just said education experience, okay? Also, one thing to point out here, we've mentioned this a few times, but if you do see some output, let's see if there's an example down here. I think there is. Here we go. No. Here we go. If you see something like e to the negative, remember, this essentially means 0 because it means move the decimal point 66 places to the left. Okay, so anytime you see that e to the negative, think that's a p-value of pretty much 0. So go back here. All right. Let's assume you want to estimate the relationship between SAT scores and college GPAs. Suppose you run the following regression. You find, here's the intercept estimate, here's the coefficient estimate on SAT score, and then here's your standard errors for both those. So these standard errors, right? If we think about Excel output, that's these, right? Standard errors of each one of these different variables. So I've got a pretty simple linear regression here. So what would the test statistic be for the SAT slope coefficient? So all we do, look at this formula sheet, take that coefficient estimate divided by the standard error, so 0.002 divided by 0.00075. So do this in the calculator right now. We should get about 2.67 if we throw that into our calculator. Okay. I could do the test statistic for the intercept here as well. Just 1.5 divided by 0.65. If you do that, you should get about 2.3 for that one. Okay. So hopefully these test statistic questions are easy points in this exam. So let's assume that that coefficient was 1.5. Okay. Which is kind of what we were given up here. So if we think about, if we plug these things in, if I'm trying to make predictions, actually, let me copy this just to make this easier so I'm going to type everything out. If I'm trying to, oh no, I want to go to, here we go, equation. And then, there we go. I want to make predictions about what GPA is. I don't observe that error term. I have my estimates here. So for beta 1, we got what? 0.002. And for this intercept, we got 1.5. Might help to kind of write that out once we're given that information. So what's the interpretation of that intercept coefficient? Well, no matter if we have multiple variables on the right-hand side or just one, the interpretation of intercept is if every x variable is equal to 0, this is the predicted value for our y variable. So if someone got a 0 on the SAT score, their predicted GPA would be 1.5. So the average, so it doesn't represent averages. So the expected college GPA for a student earning a 0 on the SAT, which is what we were saying, is 1.5. Okay. Now, if we look at answer C here, right, this is kind of the interpretation of beta 1, except for it should be 0.002. So this is kind of the wrong answer for the intercept, but if we were trying to interpret beta 1, it would be that holding everything else constant, although we don't have anything else in this regression, every point earned in the SAT, you know, 1 unit increase in SAT would be associated with a 0.002 increase in GPA. If a student earned a 1200 on the SAT, what would you expect their college GPA to be? Well, once again, once we have these estimates, you're really just talking about an equation that you can plug values into. So I can come up with a predicted GPA for any SAT score. So if you're asking me about a 1200 SAT score specifically, well, then I just plug in that 1200 for the SAT, and I just put that into my calculator. I make that prediction, I should end up with 3.9. Now, if I forget to add in that intercept, right, if I just took 1200 times 0.002, I'm going to get 2.4, right? But that's not the correct answer because I'm asking you to predict their GPA, which includes the intercept as well. So you have to add in that 1.5 as well. And then you'll get the correct answer of 3.9. Any questions on that? Assume that the test statistic on the SAT was 5.75 instead, corresponding to a p-value of pretty much 0, right? So a very significant relationship. An education researcher suggests that providing that this is evidence that if we just raise students' SAT scores by making it easier, we could, you know, result in higher GPAs in college. So what's wrong with this logic? So this is just the general idea. I've been trying to really hammer this last few weeks, which is that these slope coefficient estimates are just evidence of correlations, not causal. Right? So, you know, if it was a causal relationship, then yeah, anytime you see a higher SAT score, the GPA will go up. But it's not, just a correlation. So if I make it easier, right, it's not going to be that, you know, it's not that necessarily scoring higher on the SAT score is causing you to do better and you have a better GPA. It's that there's this underlying thing we're not observing, which is the original ability of the individual's intellectual ability. So we're looking here, we're looking for something that says, look, these are just evidence of correlation, not causation. And so the results only provide evidence of correlation. it's likely that intelligent students will do well on both. This kind of omitted variable bias, okay? I might want to go off the beaten path here. Let me see. I forget how far away we are. Where will we get today? Yeah, let's do this here. I want to add in something. So one thing I might expect you to do on the exam, when I say might, that means likely that there will be a question related to this. Let's say, assume that we include the student's parental income, right? So what income their parents make. What do you expect to happen to the magnitude or kind of the size of, and here we'll go up here so I can copy and paste it, beta 1, right? So we'll copy this down here so we have the question. So, you know, when we run these naive regressions, we said one thing we always have to worry about is this omitted variable bias. So if we look at this formula sheet, down here, we have this guy that kind of represents the omitted variable bias. So if there's some other variable, call it x2, that would influence both your independent and dependent variables, it's going to cause a bias when you try to estimate the effect of that original x1 variable you included. Right? So here is kind of the second component is really what our bias is going to be. And actually, I'm going to repost this formula sheet because something was left off of that bias. So here's our bias component. Right? So we think about this being the bias component. The variance of x1, and maybe a good example or a good idea for this would be writing this out in the context of our example. Right? So our x1 variable is SAT. So the coefficient estimate we get for the relationship between the SAT and the GPA is that. Let's say the second one was parental income. So our first variable was SAT. Our second variable was parental income. So I'm just writing this out in the context of our example. And I think that would be a good way to do it on the exam as well. Look at this general equation for the bias and then write it out in the context of your example. So this bias component will be comprised of what effect would income have if we included it in this regression. Okay? So what effect do you think income would have on someone's SAT score? Right? Now, sorry, not on the SAT score. What effect would income have on the Y variable, which we had was GPA? So if someone comes from a higher parental income, you think they've probably had more resources devoted to their education, maybe development early on in their life. And so it's likely we think if you come from a higher socioeconomic class, you're likely to have a higher GPA in college, right? There's fewer obstacles. You probably don't have to work a job in college potentially. So it's likely that this slope coefficient, if you would have included parental income in your regression, is positive, right? So we can kind of think about, if we're trying to put signs to this, well, this guy right here is probably positive. Right? What about the covariance or the relationship between SAT scores and income? Well, it'll be a very similar relationship, right? In high school, if you have more resources, right, your parents can pay to get you a tutor for the SAT. You know, you're more likely to be going to a better high school. It's likely that those two things have a positive relationship as well. And then the variance of a variable is always positive. Right? So we have three positives here. So that bias term is going to be positive. So when we get that coefficient estimate for SAT scores, right, from our original naive regression where we left income out, we'll pick up the true effect that SAT scores have on GPA, but also this positive bias amount. So if we then included parental income, we would be eliminating this bias, which was positive. So now our new estimate would be smaller. So what do you expect to happen in the magnitude of your estimate on this beta 1 variable that was on the SAT score? Or we'd expect it to go down if we were able to include parental income. So really, you know, kind of from asking a question like this, there are, I shouldn't say there's no one right answer. You know, if you for some reason had justified that you thought the relationship that income would have on that y variable of GPA was negative, then I'd be okay as long as you gave me a justification for why. So when I ask you a question like this, I want you to justify why you think the effect that that omitted variable would have on the y variable, why it is the sign you think it is, and just justify what you think the relationship is between that x1 variable that you included and the x2 variable you left out. So, you know, I think I try to give examples like this when I would think most people would expect these both to be positive. I'm not sure a story in this example you could, you know, justify why you think they'd be negative. But if you did, I would kind of take that assumption and then grade the problem based off that, you know, whatever you assume. Okay, so it's really just trying to sign this bias component that you know exists when you omit an important variable. I got a question then. How did you know it was a positive? So we're just assuming, right? So when I'm thinking about just in general, like even not for this specific problem, right? Beta 2 and then the covariance. Beta 2 represents the relationship between the y variable and whatever variable x2 was left out of the regression. So in our example, that was parental income. The covariance, remember, that's just the relationship, the correlation between the variable you included, which for us was SAT score, and then the variable you left out, which was income. When I ask you this on the exam, you will have to give me a justification or just an assumption of what you believe the sign of these is. Now, is there a right answer in the sense that in the real world that we know it? Yeah, I mean, we probably can find it somewhere. But in terms of on the exam, as long as you justify, like give me just like, I think it's negative because this, that's okay. As long as you justify it, I would accept either kind of the positive or negative for what you're assuming these components are, right? Then based off of what you told me you assume that those relationships are, then I will grade it based off like how you sign this entire bias component. Does that make sense? Okay. I know when I went through that one at first, I just kind of talked about it as though we know obviously the income. We don't obviously know that. It may be something I know because of things I've read, some research I've looked at, but in general, I'm asking you, just look at that equation, give me an assumption about what these two components are, and explain to me how that would kind of upward or downward bias your estimate for that variable you included. Okay. All right. This is good. I'm glad you asked that question. Okay. So here we have a few. Well, let me see. We might skip around here so we get a little bit of everything right there. Already went through that one. We'll do that one Wednesday. Here we go. Let's do this one down here. So number 24. Okay. So we've got this regression equation, which is sales, and we're measuring this in dollars, right? So sales measured in dollars, that coefficient beta 1 is on advertising, beta 2 is advertising squared, right? So just the advertising variable but squared. Okay? I asked you to draw a graph about what you think the relationship between sales and advertising might be, label the X and Y axis, and a brief description of why you think that relationship looks the way it does, right? And if that relationship in fact looked that way, what would the sign of beta 2 and beta 1 be? So here what I'm asking, we talked about if we include this quadratic to allow a relationship to be non-linear, really what we're thinking about is if I'm looking at the relationship, oh, got stuff from my last class, so I gotta erase that. If we're thinking about the relationship between sales and advertising, right, so I've got sales is my Y variable. Right? That's what's being driven by how much money is being spent on advertising. So what I would want you to do in a question like this is you draw what you think the relationship is. If you thought it was linear, this is actually a good point. So if you thought it was linear, that for every, the very first dollar spent, going from 0 to 1, then that effect from $1, the very first dollar of advertising, the effect that would have on sales, if you think that's the same as the dollars spent after you've already spent $1 million, right, then you would think that it's linear. Right? It's always the same. It doesn't matter how much I've already spent, $1 increase would always have the same effect. If you believe that, then really this is kind of a tricky one because we hadn't went through an example like this. So we'll call this advertising and then advertising squared. If you thought the effect is always the same, but it's positive, in this situation, I don't know, you guys are in a business college. If you can explain to me why spending more on advertising actually decreases your sales, you might have a, I don't know, you're probably not doing so hot in your marketing classes. So, so we've got some advertising here. We probably expect that as I spend more on advertising, I'm driving my sales up. That's the whole point of advertising, right? But if I think that this effect is linear, what I'm really saying is this squared term would actually be 0, right? There's no curvature to this line. It's completely linear. Now, I doubt that's the case, right? And I would think that if we're thinking about, and I think with $1, it's hard to think about what the effect of that would be. But let's think about the effect of spending like the first $1 million, and then after I've spent, say, 50 million, what's the effect of going from 50 to 51, right? An additional 1 million there. Well, I would think that initially the first $1 million, right, would increase my sales quite a bit. Right? I'm going from not letting anyone know my product exists to like getting quite a bit of people to see it, right? At that point, spending more and more, well, I'm picking up, it's like that as I spend more money in the advertising, I've already picked up the people who are pretty likely to buy my product. So spending more and more on it, it's less likely that advertising is effective. And I'm probably seeing a relationship that looks something like this, where the first $1 million spent increases Y by quite a bit. But the 50 to 51, that additional $1 million probably isn't increasing Y by much. So if this is the case where I'm increasing at a decreasing rate, right, then I would expect that quadratic term to be negative. Right? So there's still a positive relationship, but as advertising gets higher and higher, that effect is kind of being, pushed towards 0, right? Or kind of reduced. Now, if you would have instead, for some reason, it's fine if you would have thought this, maybe there's a story you could tell where even spending the first $1 million, you're not even competitive with other large companies, if this is a very competitive industry. So maybe you think that the effect of the first $1 million isn't very much, but once I get up here, spending an additional $1 million, well, now I'm competing with, getting kind of playing this arms race game with the other large companies. And so maybe you could justify why you think it's positive. Now, when it comes to these justifications, I'm not going to be grading the justification. As long as you explain to me that you believe the relationship is increasing at an increasing rate or increasing at a decreasing rate, then that's okay. I'll take that justification and grade what you think the sign should be down here accordingly. So if instead you had thought this was the relationship, so spending more on advertising is still increasing sales, so the first coefficient is still positive, but you thought it was doing so at an increasing rate, well, then you would have believed both of these were positive. Right? So this is I would want you to kind of draw what you think that relationship is. If you think that it's increasing at an increasing rate, both those coefficients should be positive. If you thought it was increasing at a decreasing rate, this one should have been positive and this one should have been, the squared term coefficient should have been negative. Okay. Any questions on that one? I would expect that there could be, so don't. Okay. All right. Let's see. So we've got kind of a different one. I think we'll save the log stuff for next class. I think we'll end it there. I think we went through quite a bit. In fact, my guess is we'll be able to get through the rest of this on Wednesday. I may even bring in a couple of additional problems on Wednesday that we'll work through, but I will get up another file of questions that we can work through together on Friday. So if you have time to go through those this week and you ask very specific questions about anything that I post in that additional kind of set of questions, it'll maybe look a little bit less like a practice exam and a little bit more like just some problems and some things to kind of work through or look through. Then make sure we have whatever questions you have I can start out with on Friday. And even if you work through some of the ones that we did today and you have additional questions on them Wednesday, I'll be willing to go through a problem again and explain it a slightly different way. Or if there was a part you didn't understand, maybe you understood today but you didn't when you were working through the practice exam, we can review that as well or go over that as well. Any other questions from me? kind of end it here for today. Okay. Like I said, I'll try to get those individual assignments graded here tomorrow. I'll post up that additional set of questions tomorrow at some point as well, maybe tonight, but I don't want to promise that, or this afternoon. And then other than that, I think we should be good. So if you have any other questions or if you're working through these, feel free to email me. I'm kind of open to set up Zoom calls all this week. Even next week, even though the exam will be available Monday to Wednesday, if you haven't started it yet and you have questions early in the week, Monday or Tuesday, that you want to email me or meet via Zoom before you take it, let me know. Try to let me know in advance so we can set something up, okay? All right, if there's no more questions, we'll end it there. And I'll see you guys on Wednesday.